Back at the very beginning of this course, we talked about the notion of a sample and how a sample compares with a population, and the necessity of having samples available to us or taking samples in order to make estimates about the population. Well, we're ready to make such estimates right now. We're ready to take samples and take information from samples and take that information and apply it to populations in a very particular kind of way. Before we do that, though, we want to get straight on a little bit of vocabulary that'll help us in that process. The notion of population and sample we've talked about before, population being a set of measurements, or we can think about population in that way. Sample is a subset of population measurements. And the best kind of sample we can have is a random sample. Well, the notion of parameter, the word parameter refers to a numerical descriptive measure of a population. So the idea of parameter is married to the notion of population. And parameters would include mu, the mean of a population, this sigma, the standard deviation of a population, and p, this probability of success in a binomial distribution of a population. Well, contrast that with the word statistic. Statistic is married to the idea of sample. So same ideas, but applied to the notion of sample. Statistic is a numerical descriptive measure of a sample. X bar, the mean of a sample. S, the standard deviation of a sample. P hat, which we haven't talked about before, but this P hat is the sample version of this P over here for the population. We'll find that P hat is roughly estimated as R over N, but at any rate, it has to do with a sample, and that's the point here in talking about the word statistic and contrasting that with the word parameter. Now, parameters are fixed quantities. They are fixed because there is one single population. On the other hand, statistics are quantities that may vary, and I've written that down here. They are quantities that may vary, and that's because there are many different samples that can be taken of a given size from a population. So from one sample to the other, we would have a different X bar, we would have a different S, and so on. Okay, so these may vary. Parameters are fixed quantities. Generally, we are interested in taking information from samples. We are interested in using statistics, the information from samples, statistics, and using those statistics to make inferences about parameters. Parameters, information having to do with the population. Now, this statistics giving way to inferences about parameters can take, there are two realms that we're talking about. There are certain estimates. One of them would be the obvious estimate of saying, okay, let's take a sample and we're going to use the sample mean to estimate the population mean. All right, that's one thing that we're going to do a great deal. But associated with that is the notion that the reliability involved in that estimation process is a very important idea in that inferential idea. So we're talking about making an estimate, and we're talking about making calculations according to the reliability of those estimates. And I'll get into particulars about that in just a little bit. But just to realize that there are two areas that are, I think, of equal importance here in dealing with this idea of taking statistics and applying statistic information to parameters. Okay. Now, an important idea in making this transition from statistic to parameter, information from statistics to parameters, is a sampling distribution. Now, here's what a sampling distribution is. It's a probability distribution for the statistic we are using. All right, well, that sounds simple enough, but gee, what does that mean? Well, it's so important to understand what this sampling distribution is that I'm going to belabor the point just a little bit. And I'm going to show several illustrations of this. In this section, I'm just going to show one general illustration, and it is this. So let's say that we have an X distribution. X distribution, this is for a population of the random variable X. Okay, and it looks like a normal distribution, doesn't it? Sure. Okay, now let's take a sample of some size, and let's say that this population distribution is really, really big, like 1 million or 10 million, whatever, but really big. Okay, so now we're going to take a sample. Let's say the sample is of size 500. All right, we take that sample of 500 and we find its mean. It's X bar. All right. Now, where would you expect the X bar to fall in this X distribution? Well, gee, if we have taken values of X from all over this X distribution, we have calculated the mean of that sample, then chances are it's relatively close to mu. Let's say it's O right here. So this then is a spot for an X bar. All right, now I'm thinking in terms of left to right. The up and down business is not. There are values here, quantitative amounts here along the horizontal axis, and I'm just picking a quantitative amount left and right. The value up and down is not terribly important. We get into that up and down idea because due to the notion of probabilities and area under the curve and all that kind of stuff. All right, but all I'm doing is positioning an X bar here. All right, now let's say I go out and take another sample of the same size, 500, from the same population. Now that second X bar value might be somewhere else. That is, it could be over on this side of mu. So here's another X bar. Let's take another sample and the X bar value. Maybe it's right here, and another, 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 and another. And if I take as many as I can take, and I can take an awful lot, if my population was a couple of million to begin with, I can take an awful lot of samples of size 500. Now, every now and then I might get an X bar that falls out here. Might get a couple right in here. Might get one that falls out there. But I would get an awful lot of them, I would think, that would fall relatively close to mu. And in fact, I might find a couple that fall right on mu. If I happen to know mu ahead of time, that would be real helpful, but generally I don't. I mean, if I knew mu ahead of time, what's the point in taking a sample and then taking the sample mean? After all, the sample mean is used to estimate mu. So, all right, so presumably we wouldn't know what mu was. Now, a lot of times in our examples, though, just to discuss the idea about the relationship between mu and X bar values, we're going to assume that we know the value of mu. But in real life, we really don't, do we, generally? Okay, so because we are calculating the X bar values, and the X bar values are probably going to gather themselves relatively close to this mu. Notice the distribution of X bar values and how they're kind of collecting themselves or nesting relatively close to mu. Now, that will create a situation where we will have a probability distribution of X bar values. Now, that's what a sampling distribution is all about. Now, I'm using X bar as an example of sampling distribution. There are other sampling distributions, but the X bar distribution is the one that we're really going to concentrate on rather heavily. And that distribution, if we overlay the X bar distribution on top of the X distribution, it would turn out to look something like this. Now, I'm trying to draw this in a way that I have that the total area under this curve that I'm going to draw is 1. This is supposed to be 1, and so I want this distribution that I'm drawing for the X bar distribution to be 1 as well. So it would presumably kind of have this kind of shape, and it'll turn out to behave something like this. And we're going to find out that as we might expect, gee, if we took, I don't want to touch right here, if we took all of these x bar values and took the mean of all of them, then the average of all of the x bars would be exactly mu. And that's what we would expect. At any rate, I don't want to mislead you here and think that we don't have values all over the place in this x bar distribution, so I'll put a few more in here. But it's the idea that we have a distribution of x bar values, and that is what a sampling distribution is all about.